Welcome to Kognito Key. I am so incredibly excited to dive into today's explainer because we're going to break down exactly how computers store data right at the hardware level. If you've ever wondered what makes your devices tick from the inside out, well, you are absolutely in the right place. We've got a lot of ground to cover today. We'll start with semiconductor basics, look at their internal organization, and then break down the massive divide between random access memory and read-only memory. So let's kick things off with the foundation of literally all modern computational devices, semiconductor basics. Almost all memory units today are carved out of semiconductor material, and primarily we're talking about silicon. This is the incredible stuff that has allowed engineers to drastically increase storage capacity over the years, while simultaneously driving down the cost per bit. It's the whole reason we have such large, affordable main memory today. But what's truly mind-blowing here is the performance. The cycle time, which is the time from the start of one memory access to the start of the next, ranges from 100 nanoseconds down to a blazing fast 10 nanoseconds. Just try to imagine that level of microscopic speed happening continuously inside your phone or laptop. It's wild. Okay, moving right along to internal organization. Let's zoom in microscopically and look at how this silicon is actually structured inside the chip itself. I want you to think of the internal memory circuit like a highly precise grid. In a standard 16 by 8 array, you've got 16 word lines, numbered W0 to W15, intersecting with 8-bit lines, B0 to B7. And each specific cell at these intersections holds exactly 1 bit of information. Now, the absolute crucial point here is communication. Memory cells in the exact same row connect via a common word line. Meanwhile, all the cells in a single column connect to a sense and write circuit via 2 bit lines. It's this brilliant architecture that seamlessly handles all the data input and output across the entire chip. With that physical grid in mind, let's look at our first major category of semiconductor memory, random access memory, or RAM. The defining characteristic of RAM is volatility. See, RAM is incredibly fast, but it's totally volatile. It holds information only while the power supply is on. It'll forget everything the very second your device loses power. This is the direct opposite of non-volatile memory, like ROM, which remembers your data permanently, power or no power. Now, digging into RAM itself, we have a really fascinating trade-off. You can use static RAM, or SRAM, which relies on CMOS transistors. It keeps its content as long as the power is on, making it super fast and low power. But because it needs several transistors per cell, it's pretty expensive. On the flip side, we have dynamic RAM, or DRAM. This is much cheaper and allows for higher density memory, simply because it uses much simpler capacitor cells. But here's the catch with dynamic RAM. Because it relies on those simple capacitors, they can only hold a charge for tens of milliseconds. They actually slowly leak tiny amounts of current, measured in picoamperes. So your system has to constantly execute a process called refreshing. It's continuously reading or writing new information just to fully recharge that capacitor before it completely loses your data. It's literally working behind the scenes nonstop. All right, let's switch gears for a second and explore the other side of the hardware family, the permanent, non-volatile world of ROM, or read-only memory. Because ROM retains data without needing a power supply, traditionally it's written just once during the manufacturing process. Since it can't be easily rewritten, it's the absolute perfect place to safely lock away the vital, small system programs your computer relies on just to boot up and function correctly. Over time, though, engineers realized they really needed more flexibility, and that led to a fascinating technological evolution. We moved from standard ROM chips to programmable ROM, then erasable programmable ROM, electrically erasable programmable ROM, and finally flash memory. It's an incredible journey from write-once chips to fully rewritable storage. Let's look a bit closer at those middle steps because it's truly amazing to think about. Early rewritable memory, EPROM, literally had to be exposed to actual ultraviolet light to dissolve the charge on its transistors. You were blindly wiping all of its data at once. Thankfully, EPROM came along and gave us the ability to erase and program data electrically. Though, to be fair, it did require some pretty complex circuits using different voltages for reading, writing, and erasing. And that brings us to our modern hero, flash memory. Flash memory perfected this technology. It allows devices to selectively erase and write entire blocks of cells at once. But more importantly, it brilliantly uses the exact same voltage for reading, writing, and erasing. This massive reduction in circuit complexity and power consumption is exactly why flash memory powers so much of our world today. So, I want to leave you with this final thought. When you look at how far we've come, from UV-erased chips to lightning-fast solid-state silicon with access times plunging past 10 nanoseconds, it really makes you wonder, right? What impossible speeds and massive capacities will the very next generation of memory achieve? The physical boundaries of hardware are constantly being pushed. Thank you so much for joining me today. If you found this explainer helpful and learned something new about how your devices store data, please hit that like button, share this explainer with your friends, and subscribe to Kognito Key for more structured and fascinating tech insights. Keep learning, and I'll see you in the next one.